Thank you. So digital twins are becoming increasingly used as a valuable tool in medicine, offering significant potential in precision medicine, personalised medicine. At the absolute forefront of this research is our speaker today, Professor van der Schaar. She is the founder and director of the Cambridge Centre for AI in Medicine and the chair of Machine Learning, Artificial Intelligence and Medicine at Cambridge. And I am delighted to welcome her to the stage to discuss her research and insights into building digital twins using machine learning. Thank you very much.
Thank you very much for the kind invitation. Hopefully you can hear me. I hope to excite all of you just before lunch about something quite geeky, but I think useful, which is digital twins. I'm going to tell you what I believe digital twins are. We have 50 million definitions, so you'll hear my way of thinking about them. And also I'm going to try, even though I'm not a clinician, I just work with many clinicians, to tell you why I think it's an exciting technology. And then at the very end of the talk, what I plan to do is to show to you two ways in which we can build digital twins that may be quite geeky, but still may be informative and hopefully interesting. So, I'm going to try to see if I can move my slides. Okay, good. So what are digital twins? So digital twins are a dynamic virtual representation of a system. And usually what we do is we use data, often real-time data. I'm going to talk quite a lot about that. Knowledge that you may have. This can be mechanistic, physiological information, pharmacological information, or information that may come from papers. And machine learning at the very cutting edge to hopefully mirror and simulate how the real world, most interesting for you, a patient, would behave. Now, what would we like digital twins for? Everything under the sun, and not only in medicine. In medicine, we would like to do it for a patient, but maybe also for an organization like a healthcare system or a clinic, and why not an organ or a clinical trial? And the reason I think this is a very interesting technology, it allows you to really understand and stress test a particular set of scenarios. So if it is for you to do a digital twin of a patient, you would like to understand what are possible scenarios that could happen to these individuals, how would the patient respond under different types of interventions, and allow you to really think by yourself as a clinician, but also together with the patient about what are possible likely trajectories of this individual, possible responses to medication, and really have, with the help of a very good user interface, an ability to do scenario planning. And if it is for us to really think about something that we use routinely, which is Google Maps, try to see really a variety of scenarios that could bring us from one particular state that the patient is to a variety of possible states under possible types of interventions, and discuss together with the patient whether this is really the right route to take. Now, I think this is quite important because part of the reason machine learning is not that prevalent in medicine is also because we don't stress test enough machine learning. So this is important. Digital twins are important for machine learning itself, but I think they are very important for medicine. And I put here a plane because often you would not like to board a plane that was not stress tested enough. Granted, we know that in recent years, Boeing has cut corners with this type of testing. But I would argue that even I, as a patient, would not like to be in the hands of you, a clinician, just like that. I'd like you to stress test the different scenarios if I'm really sick. If I have just a flu or something simple, maybe it's okay. But if, God forbid, I get cancer, I'd like you, and my mother died young of breast cancer, and I'm born in a family of clinicians, and I think many mistakes have been made. I'd like you to stress test the different scenarios. I'd like really for you and I to understand what is going to happen. I don't just one plan, I like multiple plans, I like to understand them. And this is what digital twins can help us do. So it's a new way to think and act, think as well, but action is important as well. So they are what we call generative models, and I'm going to talk a little bit about how they are different from just forecasting, where I forecast what will happen in a trajectory of disease. Here is generative model. I'm generating a variety of scenarios, and this is a harder task in machine learning. And they can simulate what could happen, not just what will happen. Yeah? So I'm not trying to just tell you one particular scenario, but I'm going to try to show you different types of scenario under different types of monitoring, different types of treatments, and try to really understand that. So I'd like to understand complex patient journeys. For instance, explore how a patient's cardiac function could evolve under different levels of activity and therapy. Maybe you finally convince your patients to do some exercise and maybe take their medication. You can test clinical hypotheses safely and rapidly, so it's really a tool for you to think about your patient. You can plan and adapt interventions with foresight. You can tell your patient when should be coming, how it should be coming to the clinic. At times, certain patients, due to their particular private situation, may not be able to come because they live far away, they may have young children. So really do this scenario planning, do this stress testing into the future. It's very important, and digital twins can allow you to do that. And again, I talk here about the patient, but you can think in a similar way about the healthcare system or a clinical trial. And often we know that clinical trials have issues. I do a lot of work on machine learning for clinical trials, and we have issues because we don't think across the entire pipeline. So what is important is that it allows you to reason about a variety of possibilities, not just uncertainties. And I think that this is really clinical thinking on steroids. It can be a tool for you to think together with your patient. Again, you can simulate trajectories of disease. You can look at possible different futures for this particular individual. Again, possibly under intervention. I think that it could be a very powerful tool for early diagnosis. I'm very interested in early diagnosis, and I think that this is really a quite useful tool where right now we are just taking, for instance, tests and trying to see, well, is this person having something after a treatment, after a symptom or a sign has already exhibited themselves. But maybe in the future, in scenarios there is a lot of ambiguity, we could really do this scenario planning and try to really generate what are the possibilities of the future, and not just tell the patient, come back in 3 months or in a year, or come back if you have this pain or that pain. We can send them home with a very clear plan of, if this is happening, this is what you should be doing next. And more generally, I'm very interested in the plumbing of medicine, trying to understand what resources we should be giving to clinics or hospitals or clinicians at what moment and when. And I had the good fortune during the pandemic to be the first geek, if you like, in this country to work together with the NHS to try to bring some of the machine learning for capacity planning in the NHS. And I think that this is very, very interesting. And finally, being able to do in silico clinical trials. We hear a lot about that, but I see very little high-quality technology for that. But this is really a big opportunity. And I'm talking here both about synthetic control arms, which would allow you no longer to need to really put people on a placebo. But I'm also talking about really this time end-to-end generation of clinical trials across the different phases to de-risk these trials and also do better the entire pipeline. And finally, I talked already quite a lot, the dialogue with the patient, which I think will be significantly enhanced. And you are going to tell me the patient doesn't want to know. I beg to disagree. We are becoming increasingly literate, and at least the majority of us would like to understand in a much more quantitative way and much more long-term way the consequences of your decisions and be sharing them. So how can machine learning help? It can build generative models. All the rage is now Gen AI, yeah? Large language models included, but also DALL-E and many others. And what's tricky here is to validate these generative models very well. So it's very easy to generate a lot of nonsense. It's quite difficult to generate correctly, especially over time and complex information. My lab has done a lot of work on generative models over time. We do a lot of work. We were the inventors of synthetic data 10 years ago. Nowadays, you hear a lot about that. 10 years ago, I couldn't sell it. Now everybody wants to have it. But digital twins is more than synthetic data, and I'm going to return to that. But the big problem in both synthetic data and digital twins is we need to validate correctly and well, and that still remains at times a challenge. I just want to put, sorry, I don't want to scare you. I know somebody told me never put equations in front of clinicians, but I'm going to do it anyway. Hopefully, it will help a little bit. So again, this is quite different. Generation is really quite different and a more complex problem than just prediction, forecasting, risk forecasting, trajectories of disease. And really the reason behind it is I really need to generate, I really need to estimate the complete distribution of data. It's not really just conditional generation like in predictions, where I'm saying given the information or the history I'm going to predict. In this case, I need to generate these many scenarios and I need to generate them with high fidelity. Of course, I may not need to generate all of them with high fidelity. I need the most likely ones or the most relevant ones, but still. Is this synthetic data? It relates to synthetic data, but digital twins are not just synthetic data. It has similarities. I take data and I'm trying to generate information, but in synthetic data, I'm having a data set that I may want, for instance, to make private. Initially, when we started with synthetic data 10 years ago, the reason I started it is I couldn't collaborate with clinicians because they had data sets that were private. And generating synthetic data with privacy preservation was key. So this is what we did. This is already long ago. We can do that really well. But synthetic data can do much more. Often I give this talk, synthetic data, first world creation, not second-rate copy. As a matter of fact, I think in many scenarios, synthetic data is better than real data, because if you have limited data, you can augment data sets, you can transfer data sets to new clinics. There are a variety of advantages to it, but this is not about synthetic data, it's about the differences between synthetic data and digital twins. When I'm interested in synthetic data, I take a data set, possibly a minimum data set, or a data set from another location, or a data set that's private, and I generate a related synthetic data set. Here I'm doing something very different. I take the history of the patient so far, and I'm projecting into the future things I have never seen. Of course, I've seen things related to this particular patient. I'm training these models on hopefully very diverse and interesting data sets. Importantly, we are finally in machine learning at the possibility of aggregating numerous data sets. So I don't need to create these digital twins based just on one data set, as glorious and as amazing that it is, like UK Biobank. I could combine biobanks. I could combine biobanks with electronic health records, with digital registries, clinical registries. So I could build these digital twins informed by a lot of data. And again, the focus is to extrapolate beyond, which is not the goal of synthetic data. Also, we are very interested in interventions and the role of interventions, such that I can do this scenario planning, which is again not the focus of synthetic data. In synthetic data, I take whatever interventions are there and try to create a synthetic data set that replicates current clinical practice. Here is about planning the future and doing this scenario planning. But there are, of course, a lot of things that we can borrow. We can borrow a lot of generative models. We can enhance them, but we can borrow them. We can deal with privacy preservation and so on. Now, let me tell you where we are in terms of building them. We are actually not as far as you may think, partially because we didn't realize the potential. This is a very geeky paper from our top conference. We don't publish in journals, but our top conferences are 40, 50 pages long, so they are serious endeavors. It's just that the world is moving very fast in our world, and for us, journals are not really relevant. But this is an example where we try to build digital twins by embedding clinical knowledge and pharmacological knowledge into these digital twins. So currently, if you look in the literature, mainly in the machine learning and in the engineering setting, I'm an engineer by training, I'm not a machine learner. So I always like to look at what the engineers did, not only the machine learners. We have quite good mechanistic models. So we have models where if you know the mechanistic understanding, in engineering we often do, in physics we often do, you may know in pharmacology. I really love pharmacology, so if you are a pharmacologist in the room, please come and say hi. We do a lot of work with them. They are very quantitative. They really understand a lot about the dynamical system that they understand. But the reality is that the human body is a little bit more complex, and often even fantastic pharmacological models are misspecified and incomplete. But in many settings, we may not even have this dynamical representation, but we may have some information. We may have some clinical knowledge, we may have some physiological knowledge, we may have some pharmacological knowledge. And this is the mechanistic information that I put on the left. On the other hand, we have this wild west of neural networks, and we can try to hybridize the two. We can try to start with a knowledge that's interpretable, and it was developed by a scientist, a medical or clinical scientist, or a physicist, if you are in if you are in the area of finance, somebody in finance, but then hybridize that to deal with model misspecification and with things that are not modeled by this relatively simplistic, interpretable and powerful, but relatively simplistic model. So we do hybridization. This is something we do for quite some time, but we do it now for digital twins. And what we do in effect is actually we take human expertise and we deal with the complexity of the human body by doing this hybridization, and we learn that from data. So this hybrid component, this hybridization, is not only based on knowledge, but also based on data. And this is why we call them hybrid digital twins. The machine learning model, though, is not going to be neural networks. That's the past. The future is Gen AI. So we use large language models and agentic large language models to help us build these digital twins. And here is where I hope I'm going to get you interested. Forget about this slide. I'm going to work through it. But I want to tell you why you, the clinicians, are suddenly in the front row. When we were doing deep neural networks, you could go to sleep or watch your favorite Netflix movie because there was very little you could do. You need to help your favorite friend to tune your hyperparameters, like was asked here, or use a copilot. But now with agentic frameworks based on large language models, you can converse with these models. You no longer need to code. You are able to have an interface which works with natural language, like you are conversing with your favorite chatbot, whether it's Claude, Perplexity, or ChatGPT, or Gemini. You are conversing with these tools through natural language. With these agents, based on which we build digital twins, you can converse on the basis of language, and you can build your digital twin on the basis of such know-how. How do we do that? Through a series of steps. So we have quite a large number of steps. In the first part of the step, we start with some modeling knowledge. This could come from physiology, but it could also come from pharmacology or a variety of it, or it could come from some papers that you think are relevant. After that, what we are going to do is we are going to let the large language model ingest this information, similarly like you right now are prompting it, but it is actually a lot more complex. So what's happening underneath, not for you, what's happening underneath. So we have this LLM agent ingesting this knowledge which you give, and on the basis of it, it's going to try to improve underneath the symbolic code that it is generating for the digital twin, as well as the neural network code that is generating for this digital twin. Then we are going to evaluate this digital twin on some data that you held out, to make sure that actually, indeed, the digital twin is generalizing, is of high quality, and indeed, things that it tries to generate do happen, are within the support of what you see happening to this particular individual. Of course, we are generating a lot more scenarios than what you have in your data set, but what you generate should also include what did indeed happen to this individual, if indeed these interventions were done. Then we are also going to evaluate this agent based on other information, such as papers, such as maybe your own feedback you are giving to this digital twin if you don't like something, and that is in an iterative loop. So you are able, with through interaction through language, to steer the development of this digital twin, as well as evaluate it potentially on different types of patients, different types of data, as the process continues. I hope I give you a feel of the fact that now you have, if you like, a co-pilot that you are training through your know-how, through papers, your knowledge, your patient data. Again, we don't need to put this data into these large language models. You can make architectures that keep your data private. So don't be afraid that OpenAI or DeepMind is going to steal your data. There are ways now to keep this data private. So, but you are in control of building this agentic framework, And maybe you can include other things. This is a relatively simple one, but you can decide what variables you want to include, what variables you want to exclude, over what time horizons you'd like to model this, what type of interventions you want to build. So this can be done in conversation with this agent, large language model-based agent, which takes your information and underneath builds code. It builds code, it builds both a neural network as well as is evolving your mechanistic model. But this is great, and we have starting to debug that. And if you are interested in this, please reach out, because we would like to collaborate with clinicians to really build something useful. But there are some issues with it. Digital twins struggle at times because we not only have current data. In the previous case, we have current data, and given current data, we show what's happening. But the reality is that you may have new interventions. Potentially, I work quite a lot in cystic fibrosis. Fortunately, cystic fibrosis, even though it's a nasty disease, has a lot of movement in the last years. We have a lot of new drugs. For instance, ivacaftor is such a new drug. So if we build digital twin based on old registry data, they will not be very efficient, because we have now a new treatment, a new way of dealing with patients. So you need to take these new advances in medicine and put them into the digital twin. So the question is, what happens if you have new data, new actions? How do you really evolve these digital twins? So hence, we need to build digital twins which are flexible in terms of the amount of data that we put, but also allow us to continuously learn. As you have more data, either about the cohort, about the disease, or the individual. And why not let the individual add additional data, maybe from wearables or from their behaviors, from taking the medication or not. So more recently, we tried to build such a continuously updated digital twin, and also to kind of eliminate the need for a mechanistic model, because we realize not always, not in all diseases, such a mechanistic model or physiological model exists. So the idea is to build again an agent, but which this time does in-context learning. So what do? And in view of time, I'm going to kind of, we take data, we take a lot of medical knowledge, and this medical knowledge can be curated by you, the designer of the digital twin, or it could be a more general search of information that you have. And then every time you have a change in the environment, for instance, a new